You ever held your hand out the window of a moving car and tilted it up to make it fly? That's lift. That's how airplanes generate lift. The idea of blown lift is you can enhance that by blowing air over the hand to make it generate even more lift at really low speeds.
The idea of blown lift, that in itself is not a new concept. NASA pioneered this in the 1960s. The Air Force did some demonstrators in the 1970s.
By putting the motors right in front of the wing is being bathed in all this high-speed air. And so even though the airplane's not moving because the propellers are blowing the air, the wing sees high airspeed and it makes lift even while we're sitting still.
It's been around for decades. We've incorporated blown lift in amazing airplanes like the C-17.
The problem is you just couldn't do it efficiently and easily in the old days of piston engines or jet engines because they were complex and they were expensive.
It's never really been practical until the emergence of electric propulsion to make this a cost-effective commercial aircraft. But lightweight electric motors and functional hybrid systems are finally good enough to make hybrid electric blown lift viable, and the time has come for that technology.
What's changed today is the advent of electric propulsion, particularly what we call distributed electric propulsion.
Distributed electric propulsion allows us to distribute the propulsors across the wing in an efficient and effective manner.
It makes it feasible to have a large number of propulsors, like 8 here, on the wing.
This started as a student project. There was a group of us at MIT proving this idea of the effectiveness of electric propulsion for blown lift. And we built a subscale aircraft in 2019, which was the first proof of concept. So all that work that was going on at MIT transitioned over to becoming the Electra team that did the early design and then the development and flight test of this aircraft. The reason we use hybrid electric technology is because batteries have come a long way, but they're still not a great way to store energy. So this battery holds about as much energy as this cup of jet fuel, which means if I wanted to replace all the jet fuel I needed to fly hundreds or thousands of miles, I would need a lot of these batteries, and it would make the airplane way too heavy to take off or carry enough energy to fly any sort of useful mission. It's an electric aircraft because we use the electric motors for the blown wing technology. And then we use the hybrid technology to get the best of both batteries and jet fuel to enable the ultra-short takeoffs and landings and have the really long hundreds of miles ranges that the market requires. There's a reason that almost everyone has flown on an airplane and almost no one has flown on a helicopter, and it's because airplanes are really cost-effective ways to move things through the air.
In building a lot of these vertical takeoff and landing aircraft, we really showed that though it's a great capability, it comes with a lot of cost and complexity. And being able to provide the access of VTOL is what we were really after. And so we stepped back, we really questioned the assumptions, and found that if you give yourself a couple hundred feet of takeoff and landing area, that you can make a real airplane that has the same access, but also has 2 times the payload, 10 times the range, and is a lot more affordable.
We know there's a market opportunity because it already exists. Now you just need to have an aircraft that can serve it more cost effectively and be able to provide it to a greater community. And that's what we're building. A vehicle that can use very small infrastructure that is affordable to build, and a vehicle itself that has low operating cost. Aviation is a nodal network, meaning every point is connected to every other point. And today, we're limited to about 30 hub networks, major airports that have service. There's 5,000 general aviation airports out there, which if you can serve cost effectively, you can add those to this nodal network and connect to all of them. And really what we're going to do even further is, since we only require 300 feet of runway, we're going to add tens of thousands more to communities that don't have them today and connect them to the rest of the country and the rest of this network.
Designing a fixed-wing aircraft that can take off and land in a football field is an amazing thing.
You now don't have to go through the airport anymore. You can take off and land in a parking lot, from a piece of road, from a barge, any number of spaces. That means you can put a lot more of these wherever you want.
We are bringing together a number of technologies that have been proven individually, but never integrated onto a single platform. And that is the purpose of the EL2 aircraft behind me. You could not have built this aircraft more than 5 years ago because we did not have the batteries to enable hybrid electric propulsion train like this. So today, because of the electric technologies that are being developed and matured, we can make this whole new powertrain that achieves this level of performance and fundamentally unlocks the ultra-short aircraft and industry.
The VL9 is the unlock for the era of direct aviation.